All right, are you ready for the big one? Work in an open system. Now, up until now, we've considered work and energy. We've considered all the different forces that are acting on things, but it's been in a nice little safe, closed system where there's no friction, there's no applied force, anything like that. Now we're letting it out into the wild, where such forces exist. So it could be something like a car driving up a hill, for instance. Where you've got now an applied force pushing it up the hill and probably friction pulling it down the hill, along with our usual suspects of gravity and normal. Remember, gravity is always vertically down and the normal is always perpendicular to the plane. Now, let's have a quick think about what's going on here compared to what we used to. Still the energies apply that we used to, so it has got some initial potential depending where it is on the hill and kinetic, and we could equate that to the final and the final potential and kinetic, but not in isolation, obviously, because it's not a closed system anymore. So let's have a look and see what other forces are at play here. We've got the FA, which we know is definitely adding something to the system. You could consider it to perhaps be helping, okay, to get the car up the hill. So it's going to be adding positive work in this case. And then, sorry, on the other side we've got friction, which is definitely hindering, which is negative. So looking at the work done by the applied force, is it an input or is it an output? Okay? In other words, on this equation is going to appear on the left or on the right. Now, what we're doing here, by the way, is just a little derivation of trying to work out where this Wnet and Wnc and all these equations that you have to use, where do they come from? It's not a purist derivation, so don't shoot me down if you're a brilliant mathematician, but it helps to understand where things come from. I'd say the work done by the applied force is an input, so it's going to appear along with the initial things on the left-hand side. Whereas the work done by friction appears as an output. So that actually would work pretty well as an equation. All the stuff that we put in, what it initially had, plus the energy of the engine, is what we end up with, plus the work that was lost due to friction. Okay? We can then rearrange things. I'm going to ditch the colors for now, but put the works together on one side, and then group the EPs and the EKs. So you can read my scrawly handwriting. So in fact what we end up with here, this is the work done by the non-conservative forces. Remember, the conservative force, the only conservative force, is the force of gravity. The others are the ones that broke our little bubble. Friction, applied force. These are the non-conservative forces. They are the culprits. All right. So the work done by non-conservative forces, Wnc as we sometimes use it. Not everyone's been taught this, so if this is a blur to you, just smile and wave. If it's useful, use it. This is the difference, or rather the change in potential energy. Final minus initial. And same for kinetic. And in fact, that equation appears on your sheets. Many of you wouldn't have even used it, but it is right there on your formula sheet. Wnc equals change in EP plus the change in EK, which means the work done by our non-conservative forces, the total work done by those two, is actually going to be equal to the change in the kinetic and potential energy of our object. Okay. Now the reason I wanted to sort of tee that up for you is then to say, well, what about that work-energy theorem that we use all the time? Okay, because that's only got delta K. And how does that work? What happened to the delta P? Well, just to understand delta P, delta EP, change in potential energy, that's a very interesting little quantity. And there's a very useful shortcut that I want to show you quickly just before we get into our other calculations. If we considered an object, say, falling down through a height h, okay, with just the force of gravity acting on it, the work done by gravity is the force times the distance times by cos of theta. Now, it's in the same direction, so theta is 0, therefore cos of theta is 1. Fg is mg. the delta x that it moves through is h. So in fact, the work done by gravity is equivalent to the potential energy. But it was the potential energy that it lost, because it had EP up there, and then it actually lost it on the way down. So you'll see often in calculations that these two are going to be equal but opposite in a magnitude. If the gravity does positive work, it's because the potential energy was lost. If potential energy is gained, it means gravity had to do anti-work because it was acting in the opposite direction. Okay, so because of that, I want you to see that this little guy here, we can actually put across to the other side and not just get the work done by non-conservative forces, but get the work done by all the forces, including gravity. We've already considered these two. Normal, as we heard previously, is the laziest force. It never does any work, so we don't have to worry about him. And gravity, we're now putting in to get the total work done, and then what we're left with is delta K, or delta EK. And there's our work-energy theorem. So as I said, it's not a purist derivation, but at least hopefully it'll give you some understanding of where these things come from. Now, more usefully perhaps, let's have a look at the way that we can approach actual test questions, exam questions, and how to tackle those. As I said, the challenge in this is not so much the maths, the challenge is the thinking, where to begin. So I want to give you a little tool. Oh, I might have left the diagram, never mind. I want to give you a tool to help you process the way that a calculation will actually flow. So let's keep our little example. Let's keep our little car there. All right, with FA, FF, FG, FN, and let's use that as a working example. This section where we're dealing with open systems orientates all around this Wnet, the overall work done on the particular object. And there's various ways that we can calculate Wnet, and that's what this is going to be all about. So this little tool is there's three different ways. The first way is draw yourself a diagram and look at the forces that are acting, because if we want to know about work, well, we've got to know about forces, because work is force times distance. So look at all the forces. So a force diagram or a free body diagram is absolutely fine, and we're going to make a sum of all the different works that are there. So in our case here, we've got Wnet is equal to work done by the applied force, work done by friction, work done by gravity. And we could add in work done by normal just to have the whole picture, but as we said, it's not going to be there because it doesn't do any work anyway. So that's one expression for Wnet. Let's zip around the circle and see what else we've got. This second one, we don't use that often, but if you happen to know the net force, well then you just plug that into the equation and that'll give you Wnet, our usual work equation. And the third way is the one that we just derived in the previous example, which is the Work-Energy Theorem, where Wnet is equal to delta K, or delta EK. Now those three methods are all different ways to calculate Wnet. And depending what information you're told, you'll be able to bring two of them together. It's usually these two, okay? So all the information that you're told about forces and distances and thetas, etc., will help you populate this one. And this one down here, well, you'll need to know about masses and perhaps initial velocity and final velocity and things like that. And typically you'll maybe have all the information here and you're trying to find the friction, or you'll have everything here and you're trying to find the final velocity. So what I'm trying to show you is that it all orientates around Wnet. So the way that then we would then do the actual question, Wnet always says, and it puts it in big capital letters so you can't ignore it, it says using the work-energy theorem. So in other words, don't be a dwarf and just start with the work-energy theorem. So the first thing you write on your paper is that. Okay, so your first piece of working can be that. In fact, I'll show you in a written example how we can actually do this one. That might be the easiest way to see it. So take a snapshot of that on your screen. This is the sort of the basic tool that we're going to use in terms of your thinking and your planning and how you're going to bring the different pieces of information together. There's one last thing before I leave this little diagram. Remember I said we were expecting the FA to help, which means this is likely to be a positive value. FF is always going to be hindering. It's always opposing motion. So that is, we're expecting to be a negative value because of the cos 180. And in this case, FG is actually hindering as well because it's trying to go uphill and the gravity is pulling it down. So we're expecting that also to come out to be a negative value. So just so that you sort of got a pre-warning as you begin to do the calculations, you know what to expect as you go. All right, let's have a look at a question. It's also from that same 2009 paper that we did Tarzan from. And it's question number 5, the chap in the wheelchair. So if you want to turn to that, whilst I clear some space for us. Okay, so John applies a force F to help his friend in a wheelchair to move up a ramp of length 10 meters and a vertical height of 1.5 meters as shown in the diagram below. The combined mass of his friend in the wheelchair is 120 kgs. The frictional force between the wheels of the wheelchair and the surface of the ramp is 50 newtons. The rotational effect of the wheels and the wheelchair may be ignored. The wheelchair moves up the ramp at a constant velocity. 5.1, what is the magnitude of the net force acting on the wheelchair as it moves up the ramp? Give a reason for your answer, and that is 2 marks. Okay, so I hope you were following that as I was rubbing. So basically, this guy's pushing his friend up a ramp in the wheelchair. John is the chap pushing. The length of the ramp is 10 meters. Height of the ramp is 1.5 meters. Mass of the wheelchair and the guy in the wheelchair is 120 kgs. Friction is 50 newtons. Okay, so let's get our head around what's going on here. I'm just going to draw a force diagram, which allows me to put some more details rather than just the free body. I don't need to draw a fancy wheelchair. I'm just going to draw something like that. There's John's force, FA. We're told that there's a frictional force of 50 newtons. FF equals 50 newtons. There's FG. Put too much detail, so I'm just going to put mass is equal to 120 kgs there. The total distance is 10 meters. And the height, running out of space here. This way. Height is 1.5 meters. Okay, we've got just about everything in there. And the wheelchair moves up the ramp at a constant velocity. Okay. Now, 5.1 is getting you to try and pick up that key phrase in the question. Because it says, what is the magnitude of the net force acting on the wheelchair as it moves up the ramp? Give a reason for your answer. And there's only 2 marks available. In other words, there's no calculations here at all. It's simple, but it's not necessarily easy. Okay. The key phrase, if you've picked it up, I hope you have, was just snuck in right at the end there. The wheelchair moves up the ramp at a constant velocity. Now that little phrase says a lot. So look out for it. I'm going to put it down in the corner here. Constant velocity means that it's not accelerating, yeah? If it's not accelerating, it means according to Newton's second law, there's no net force on it. Well, if there's no net force on it, from our previous previous board, the net work is also naught. And if the net work is naught, according to the work-energy theorem, the change in EK is naught, which means that it's not speeding up, it's going at a constant velocity. So there's a lot of information wrapped up in that little phrase, and it informs us what we should do for 5.1. The magnitude of the net force must be 0, because he's not getting any faster. So the magnitude of the net force is 0 because it's going at a constant velocity. That would be your reason. 5.2, what's the magnitude of the net work done on the wheelchair on reaching the top of the ramp? Well, it's going at a constant velocity. There's no net work. Okay? He does reach the top of the ramp, he's gained potential energy, but overall work, well, it's 0 because of the constant velocity. 5.3, now we get into some calculations. Calculate the following. The work done on the wheelchair by force F, which is John's force. Okay, what was his work done? Well, let's pick this one up. So let's take the classic approach. We're going to start with the work-energy theorem. Okay? Next step, we sub in the stuff that we know. On the right-hand side, we know that the delta K or delta EK is 0. It's going at a constant speed. On the left-hand side, I'm going to put all my different works that I know from the diagram there. So I'm going to have the work done by John, work done by F, plus the work done by friction, plus the work done by gravity. And that's it. We can leave normal out. Question's asking for this, so I'm not going to try and break that one down. I'm just going to leave it as WF. But these ones I can. We know that, I'm just going to break it down to the algebra so you can see the progress. The work done by friction is the force of friction times by the distance moved times by cos of theta. And the work done by gravity is the force of gravity. Now, this is an interesting one. You could say it's Fg parallel times by the 10. But that's going to take a bit of extra calculations and doing sines and all that sort of stuff. A really nice little trick is actually using what I showed you on the previous thing about the work done by gravity being equivalent to potential energy. And I can say, well, the work done in getting this up the slope is the same as lifting the object 1.5 meters or dragging it up by 10 meters. The maths all works out. You can test it if you fancy. But Fg times by the height times by its own cos theta, which I'll come through in a second, actually gives us the same as Fg parallel times the full length. That's a shortcut. Try it out. This is what we're trying to find. Let's leave that. Let's bring in some values. That is 50 times by 10 times by cos of 180, which is minus 1. Put that straight in if you want. Fg, well, that's the 120 times 9.8 times by the 1.5 of the height. And because gravity is acting down and we're talking about it going up, that is also cos of 180, which I'm just going to put minus 1 this time, is equal to 0. Okay, so there's the calculation. WF is equal to, and let's flip this over to the other side, so that's minus 500, well, let's do the calculator. They both end up being positive, so we've got 120 times 9.8 times 1.5 plus 500 equals 2,264 joules. That is the work done by John. Okay, so that's the gist of it. The next part of this question is actually a whole stack easier. All they ask you to do is to work out what his force is, and you just have to put that into the normal work equation, and Bob is your uncle. So that's the gist of it. I think we'll leave it there. It's time for you to get on with your own practice. But before we leave it, just want to give you a quick sneak preview of power. As I said, it's not too bad. It's a fairly gentle landing to the whole topic. There's the definition of power, and then there's a second equation that you can use. And it'll probably be worth about 2 or 3 marks in the entire paper, so it's not too hectic at all. Power, by definition, is the rate of work. The rate at which work is done. In other words, W over T. That's the official formula. The other one that you can sub in there, basically, it comes from I'll just put it in there for you. F times delta x over delta t. X over t is the same as velocity. So that's where the other one comes from, which is P equals FV, which you can only use if you know that the object is moving at a constant velocity. So if you're asked to find the power of an object, just look and see what you know. Do you know forces and velocities, or do you know work and time? And basically sub it into that equation. Can get a little bit more complicated than that, but for now, I think let's leave it there. Cool. Have fun. Cheers.